So let's think a little bit about orbits. The moon, as we said, has a force applied to it. The Earth is attracting the moon gravitationally. And one might ask, why does not the moon fall on Earth? And the answer is that the moon is falling on Earth. Remember, moving in a circle is motion with a constant acceleration towards the Earth. Just as my little rubber ball was accelerated down towards Earth, so the moon is accelerated towards Earth with a constant acceleration. To demonstrate this idea, we go back to our pink bowling ball. You'll notice that when I hold it away from me and let it go, the Earth's gravity will always make it fall towards my head, since I'm standing under the suspension point, whatever direction I let it go in. But if I give it an initial velocity that is just right, it will happily circle about my head in a roughly circular orbit while accelerating towards the center at all times. And we also see that by giving it either a larger or smaller initial velocity, I get elongated orbits. They're the analog of elliptical orbits in the case of actually gravitational motion around the Earth or the Sun. We'll do more detailed calculations of all this later, but for the moment we understand that orbiting is just a way of falling without ever hitting the ground, to paraphrase Douglas Adams. What we saw is that uniform circular motion about the center of gravity is a solution to Newton's equations, and if you think back, this would require that I launch the bowling ball with precisely the speed predicted by the Kepler relation and its distance from the center of gravity. What happens if the initial velocity is either too large or too small? Well, as with the bowling ball, you get elongated orbits, and you will not be shocked to learn that in the case of Newtonian gravity, and Newton solved these cases, the result you get is precisely the elliptical orbits with the center of gravity at one focus that Kepler had observed for the motion of the planets around the Sun. And so you find that there are all these elliptical orbits, and in fact, there are also open orbits, like this hyperbolic one we see here, which describes the motion of an object that comes in from infinity and recedes off to infinite distance. Of course, if you start along any point of this orbit with the correct velocity, then you will reproduce the latter part of the orbit. So these describe the motions of objects that are not bound to the gravitating blue ball over there, but rather are deflected by it. We'll return to orbits like this in the future. So this is very nice, but it gets even more general than that. Newton's law is universal, so it'll apply to any two objects that are orbiting under the mutual gravity. A little more work shows that we've a little bit been cavalier. We sort of assumed that the Sun was stationary and the Earth orbiting it, or the Earth stationary and the Moon orbiting it. You should have known that there's something wrong there, because if the Moon is accelerating towards Earth due to the Earth's gravitational attraction, well, then the Earth must be accelerating towards the Moon due to the Moon's gravitational attraction. Of course, the acceleration of Earth is less than that of the Moon because the Earth is more massive, and this is sort of the situation here. A very massive object and a lighter object are orbiting under the influence of gravity. The cross that's fixed there is the center of mass of the system. Its distance from the center of each object is inversely proportional to the mass of the object, so it's closer to the massive object. It's the point at which these things would balance. But they both orbit each other. The center of each object describes a circle, so they're always on opposite sides of this circle. Taking into account this recoil, you find that in fact the distance between the two, the radius, or if it's an elliptical orbit, the semi-major axis, still satisfies Kepler's law, no matter what the object is. It has nothing to do with the Sun. The correct statement, it turns out, when you take into account the motion of the heavy object, is that the constant that relates the square of the period to the cube of the semi-major axis is in fact 4 pi squared over g times the total mass of the system, the sum of the two masses. Now, in the case of the Sun and the Earth, or the Earth and the Moon, one of them is so much more massive than the other that you can approximate the Earth-Sun mass as the Sun and the Earth-Moon mass as the Earth. This is tantamount to making the approximation that the Sun, respectively the Earth, does not move and only the lighter object moves. In cases like binary stars, or maybe when you're computing the orbit of Jupiter around the Sun, when the masses are closer to each other, then you need to apply this more careful calculation. This will be a very useful result to us, because it means that if we see any two objects orbiting each other in the universe, and we can somehow find the period in the semi-major axis, we can compute their mass. And if you look in your texts and you find the mass of planets and galaxies and stars. You might ask yourself, how did somebody compute the mass of a distant star, or for that matter, Jupiter? And the answer is, you find something orbiting it and you apply Kepler's relation. And so this will be an extremely powerful tool as we go on. All this theory, let's do an example. And let's consider the International Space Station. The International Space Station orbits at an altitude above the ground of about 370 kilometers. Adding that to the Earth's radius, we find that the radius of its orbit about the center of the Earth is about 6,700 kilometers. And so we can find its period. Its period is given by our relation p squared equals k times r cubed. And plugging in our value for k, we find 4 pi squared over g m Earth times r cubed. Notice that I've neglected the mass of the International Space Station relative to the mass of the Earth, which is a very fair approximation. And when we plug in the numbers, we find that the period is, taking the square root, we get this expression, extracting the 2 pi, plugging in all the numbers, Newton's constant, the mass of the Earth, and remembering to convert the radius of the Earth to meters to match the units in which we wrote Newton's constant, we find a period of 5,500 seconds, or about 91 minutes. The International Space Station and all low Earth satellites, or nothing was special to the International Space Station, anything that orbits at about the Earth's surface, orbits the Earth every 90 minutes. When you see satellites crossing the heavens, they all appear to move with a uniform angular velocity. This is the reason Kepler is telling us that they all orbit once every hour and a half. I hope that you're as impressed as I am with what we've managed to achieve by following Newton. We have found the fundamental universal laws that underlay the regularities of Kepler's laws. In Newton's time, what helped people appreciate this was the understanding by Edmund Halley that comets, these weird objects that would appear in the sky, move along the celestial sphere in some random direction, then disappear again, were actually objects that were in highly elliptical, highly eccentric elliptical orbits about the Sun, spent most of their time far from the Sun and invisible, and were visible to us when they came near. He used data that had been collected to predict the appearance in 1705 of a particular comet in the sky over London to within a day, and luckily he got it just right. People stepped out on the day that Halley's Comet, as it has come to be called, showed up, and the validity and the importance of Newton's result was understood. Here's a beautiful image of the passage of Comet Halley in 1986. It has a 75-year period as it orbits the Sun. Try to figure out its semi-major axis. Gravity works. We'll come back and do some more details. We have some more things to learn about how much information we can get out of Newton's theory. We'll turn to that in the next clip.